We are now on the operating system examples. And for the operating examples, it has three OS examples: the Linux scheduling and Windows scheduling, Solaris scheduling. First, we will discuss about Linux scheduling. Operating system used today to run a variety of applications and a variety of different hardware. It has the ability to manage thousands of tasks at the same time, including allowing multiple users to access the system simultaneously. And it was created by Torvalds, Linus Torvalds. There are three versions of schedulers processors under Linux scheduling. The ON scheduler versions from Linux 2.4 to 2.6. And next is the O1 scheduler versions Linux 2.6 to 2.6.2.22. And the next is CFS scheduler and the versions from 2.6.23 onwards. The ON scheduler. At every context switch, it scans the list of runnable processes, compute priorities, and it selects the best process to run, observed when Java was introduced. O does n when n is the number of runnable processes not scalable, and the scalability issues observed when Java was introduced. O1 scheduler. It has constant time is required to pick the next process to execute. Easily scales to large numbers of processes and processes divided into two types. As you've seen in the figure, the real time and the normal. The priorities from 0 to 99, it is real time. And the normal processes is from priorities from 100 to 139. The highest is 100 and the lowest priority is 139. Next is CFS scheduler. CFS means completely fair scheduler. From CFS became the default Linux scheduling algorithm based on scheduling classes. Based on scheduling classes, it has two scheduling classes. First, default scheduling class using the CFS scheduling algorithm. And the second is the real-time scheduling classes. Now, we will discuss about CPU processing time under the Linux scheduling. It has three: processing time, the nice value, targeted latency, virtual runtime. What is nice value? Nice values ranges from negative 20 to positive 19, where a numerically lower nice value indicates a higher relative priority. Tasks with lower nice values receive a higher proportion of CPU processing time than tasks with higher nice values. The default nice value is 0. And the term nice comes from the idea that if task increases its nice value from say 0 to plus 10, it is being nice to other tasks in the system by lowering its relative priority. Targeted latency. An interval of time during which every runnable task should run at least once. Proportions of CPU time are allocated from the value of targeted latency. In addition to having default and minimum values, targeted latency can increase if the number of active tasks in the system grows beyond a certain threshold. Virtual runtime. Each task using the per task variable runtime. The virtual runtime is associated with a decay factor based on the priority of a task. Lower priority tasks have higher rates of decay than higher priority tasks. For tasks at more priority, nice values of 0, virtual runtime is identical to actual physical runtime. Thus, if a task with default priority runs from 200 milliseconds, its runtime will also be 200 milliseconds. However, if a lower priority task runs from 200 milliseconds, its runtime will be higher than 200 milliseconds. Similarly, if higher priority task runs to 200 milliseconds, its runtime was less than 200 milliseconds. To decide when task to run next, the scheduler simply selects the task that has the smallest runtime value. In addition, a higher priority task that becomes available to run can preempt a lower priority task. Next is we'll be discussing the CFS performance. The Linux CFS scheduler provides an efficient algorithm for selecting which task to run next. Each runnable task is placed in a red block tree, a balanced binary search tree whose key is based on the value of runtime, where tree is shown below. When task becomes runnable, it is added to the tree. If a task on the tree is not runnable, for example, it is blocked while waiting for input-output, it is removed. Generally speaking, tasks that have been given less processing time, smaller values of rerun time, are toward the left side of the tree. And tasks that had been given more processing time are on the right side. According to the properties of a binary search tree, the leftmost node has the smallest key value, which for the sake of the CFS scheduler means that it is tasked with the highest priority. Because the red block tree is balanced, navigating it to discover the leftmost node will require OLGN operations, where n is the number of nodes in the tree. However, the efficiency reasons, the Linux scheduler caches this value in the variable RB leftmost, and thus determining which task to run next requires only retrieving the cached value. Now we will be discussing the next OS example is the Windows scheduling. It is the part of kernel that decides which task to run next. It is responsible for best using system resources to guarantee that multiple tasks are being executed simultaneously. This makes it a core component of any multitasking operating system. Modern operating systems such as SUSE, Linux Enterprise Server normally run many tasks at the same time. For example, you can be searching in a text file while receiving an email and copying a big file to an external hard disk. This simple task requires many additional processes to be run by the system. To provide each task with its required system resources, it needs a tool to distribute available system resources to individual tasks. And this is exactly what the task scheduler does. Windows schedules threads using a priority-based preemptive scheduling algorithm. In preemptive priority scheduling algorithm, every time process with high priority arrives in the waiting queue. The CPU cycle is shifted to the process with the highest priority. This is preemptive because a process that already being executed can be stopped to execute a process with higher priority. The Windows scheduler ensures that the highest priority thread will always run. And here goes the dispatcher. It is the portion of the Windows kernel that handles scheduling. A thread selected to run by the dispatcher will run until it is preempted by a higher priority thread, until it terminates, until its time quantum ends, or until it calls blocking system call, such as for input-output. For if a higher value real-time thread becomes ready while a lower priority thread is running, the lower priority thread will be preempted. This preemption gives a real-time thread preferential access to the CPU when the thread needs such access. The dispatcher uses a 32-level priority scheme to determine the order of thread execution. And it has two priority classes, the variable class and the real-time class. The variable class contains threads having priorities from 1 to 15. Note 0 is a thread that is used for memory management. And for the next is the real-time class. The real-time class contains threads with priorities ranging from 16 to 31. With the Windows API identifies the following 6 priority classes to which a processing can belong. First is the idle priority class, below normal priority, above normal priority, high priority, and real-time priority. Note there is a relationship between the numeric priorities of the Windows kernel and the Windows API. Processes are typically members of the normal priority class. A process belongs to the class unless the parent of the process was member of the idle priority class or unless another class was specified when the process was created. Additionally, the priority class process can be altered with the set priority class function in the Windows NPI. Priorities in all classes except real-time priority class are available, meaning that the priority of thread belong to one of these classes can change. A thread within a given priority classes also has relative priority. The values for relative priorities includes idle, lowest, below normal, normal, above normal, highest, and time critical. We will see it on the Windows thread priorities as shown in the figure. The priority of each thread is based on both the priority class it belongs and its relative priority within that class. This relationship is shown in this figure, and the values of the priority class appear in the top row. The left column contains the values for relative priorities. For example, if the relative priority of a thread in above normal, priority class is normal. The numerical priority of the thread is 10. Here. Above normal, and when you see the number 10, normal is number 10. Further, each thread has a base priority, representing a value in the range for the class to which the thread belongs. By default, the base priority is the value of the normal relative priority for that class. The base priorities for each priority class are as follows. The real-time priority class is 24, high priority class 13, above normal priority class 10, normal priority class 8, below normal priority class 6, and ideal priority class is 4. The initial priority of a thread is typically the base priority of the process of thread belongs to. Although the set thread priority function of the Windows API can also be used to modify a thread the base priority. When a thread time quantum runs out, that thread is interrupted. If the thread is in the variable priority class, its priority is lowered. The priority is never lowered below the base priority, however. Lowering the priority tends to limit the CPU consumption of compute-bound threads. When a variable priority thread is released from a wait operation, the dispatcher boosts the priority. The amount of boost depends on what the thread was waiting for. For example, a thread waiting for keyboard input-output would get a large increase, whereas a thread waiting for this operation would get a moderate one. This strategy tends to give good response to interactive threads that are using the mouse in Windows. It also enables input-output bound threads to keep input-output devices busy while permitting compute-bound threads to use spare CPU cycles in the background. This strategy is used by several time-sharing operation systems, including Linux. When a user running an interactive program, the system needs to provide especially good performance. For this reason, Windows has a special scheduling rule for processing in the normal priority class. Windows distinguishes between the foreground process that is currently selected on the screen and background processes that are not currently selected. When a process moves into foreground, Windows increases the scheduling quantum by some factor and typically by 3. This increase gives the foreground process 3 times longer to run before a time-sharing preemption occurs. Windows 7 introduced user mode scheduling or UMS, which allows applications to create and manage threads independently of the kernel. Thus, an application can create and schedule multiple threads without involving the Windows kernel scheduling. For applications that create a large number of threads, scheduling threads is in user mode. It's much more efficient than kernel mode thread scheduling as no kernel intervention is necessary. Fiber. It allows several user mode threads to be mapped to a single kernel. UMS provides each user mode thread with its own thread context, concurrency runtime or ConcRT, a concurrent programming framework for C++ that is designed for task-based parallelism on multiple microprocessors. Now we will go to the next OS system example is the Solaris scheduling. It uses priority-based scheduling. The default scheduling class for a process in this time sharing is time sharing. The higher the priority, the smaller the time slice. It includes 60 priorities levels. The scheduling policy gives good response time, interactive process, and good throughout for CPU bound process. Solaris uses priority-based thread scheduling, and each thread belongs to one of 6 classes. These are time sharing, interactive, real-time, system, pair share, and fixed priority. Time sharing and interactive classes have 60 priority levels. It contains several different fields. It has 4: priority, time quantum expired, and return from sleep. The priority is the higher number is higher priority. And the time quantum has lowest priority has highest time quantum and inversely proportional to priority. Time quantum expired, decrease in priority of a thread if its entire time quantum has been used up. Return from sleep, boost in priority if finished waiting for input output. That's all. Thank you.